It's not 3. Well, it is 320. It'll be 320 for about a month. And then it'll slowly turn into 220. And then they'll change it again. So all right. If you came in late, hand your homework problems in and sit down. The rest of us are having class. Thank you. See me after class if you still have questions. Correct time is 2:21:12. Anybody wants to know? As soon as he puts his homework down and gets out of the way, we will continue. Classes started 2 minutes ago. All right, here we go. I have got a beam fixed on both ends. Generally speaking, would have 1, 2, 3, 4, 5, 6 unknowns on it. We've already pretty much agreed that when we're dealing with bending, it deforms quite a bit. Axial deformations deform very little. So if we've got a combination of both of them, we'll probably be mostly doing the bending part. So we would go ahead and say there's no horizontal loads on it anyway. So I'd say you have an unknown shear, an unknown moment, an unknown shear, and an unknown moment. If it were a cantilever beam, then I could take a couple of those unknowns off and I could solve for everything that's going on. Now I'm getting ready to work with a method they call slope. Go sit down, please. Yeah, put your pop quiz up here if you're going to. I am going to need to know how much force is induced in this structure on both ends and at the reactions due to somebody causing this structure to twist on the end. And I've got enough things going on that I ought to be able to figure that out and ought to be able to tell how much moment it will take to do that, and I ought to be able to tell how much forces in the vertical direction are caused when you do that. So I'm going to show you the deflected structure. I'm going to show you that someone put a moment at A looking towards end B. A lot of these will have a lot of different points along the structure, so give them some end point names. And I'm going to try and solve for the reactions and the moments inside the beam and everything else. First, I'm going to take this structure. I'm going to pretend it is pinned at this end, release that support, and put a bending moment on it, causing a rotation at A. And I will admit that there is probably some force necessary to keep it from moving up and down. But for right now, I'm going to let it go in that direction also. So I've got a cantilever beam, which when you put a moment at A, looking towards end B, will cause this thing to deflect up by some amount. Delta 10 is a perfectly good name for it. Looks like the real load applied is M sub AB. And big delta for deflections due to real loads. It also causes a theta on end A. So used to giving these things numbers instead of names, I'm probably going to take a little while to get out of that. Not that it matters that much. When you do that, it generates inside of the structure a bending moment, M sub AB, all the way across the structure. Maybe my watch is just wrong. Yours is? M sub AB all the way across the structure. Some moments about this point, some moments about that point, some moments about that point. M sub AB is a constant across the entire structure. Unfortunately, when you did that, I watched the end of the thing curl up in the air. Not what I'm looking for. I don't want it curling up in the air. I want it back down here, not moving up and down in any direction. So I'm going to come in here and I'm going to put a unit load times R1. 1 times R1 will, of course, be the final number that we'll stick on there in order to make it not move up and down. But it's always nice to have these unit loads and their moment diagrams to work with. So I'm going to put a unit load on a cantilever beam. The moment diagram caused by unit load, if you say this is boring, that's the same thing we did before. If it wasn't such a nifty number, we were going to get out of it. And if it wasn't for the fact that we'll use it in this slope deflection method, I wouldn't do it. A unit load down causes 1 times 0, 1 times 1, 1 times 5, 1 times 9, 1 times L. Finally, it causes a moment diagram. Looks like a triangle due to a unit load. And it's too late. Number 1 direction, number A direction, who cares? The final deflection at A is composed of 2 people. The deflection at A due to the real loads, plus the deflection at A due to a unit load at A times the reaction at A. And the final answer for how much is supposed to move is no movement at all. So as before, I have a real structure, which I have turned into a released structure or a primary structure. I let the thing move wherever it wants to, and then I make it fit back together. Delta A0 would equal to, you could obtain that by integrating this moment diagram, start next at the left end if you like, with this moment diagram. Starting at that end, now you have to, once you've decided to start X on this end for either one of them, dx over EI. You're welcome to integrate it. I still got a couple of people who don't like volume integrals. I know a lot of people who don't like them. They think they're more trouble than they're worth. But I kind of like them. I'm going to integrate a constant with a triangle. If you want to know the integral of a constant with a triangle, it's the length of the beam times the height of the triangle's end and the height of the rectangle's end over 2. So I'm talking about getting LAC over 2. I didn't write it down. Let me write it down here. L is the length of the beam. That's this guy here. The height of the triangle is L. That's this guy here. And the height of the rectangle is the moment that you applied, M sub AB. That's this guy here. Cut in half, and of course the volume integral tables don't have the EI because they're not really deflections, they're volumes. So it's equal to M sub AB times L squared over 2EI. That's how bad your beam moved off of the support. Sorry, it should be on the support. Now then, I would like for you to put a reaction at A and cause it to go down as much as it unfortunately moved up. Let me tell you how much it moves up just due to a 1 kip load, and then we'll go ahead and multiply that times R to get the final answer for R. It's equal to the integral of a real 1 kip load integrated with a unit 1 kip load, dx over EI. The length of the beam is L. The height due to the real load is L. The height due to a unit load is L. And I have no idea. Triangle with a triangle both facing the same way, LAC over 3. LAC over 3. And then I need an EI. So the deflection at the end of a cantilever beam due to a unit load is L cubed over 3 EI. You told me that it wasn't acceptable that the deflection at 1 be anything, so you set it equal to 0 is equal to delta A0 m sub A B L squared over 2EI minus how much deflection you got due to a unit load, L cubed over 3EI, times how much is really there, some multiple of 1, and you solve for R1. Now, that's in the table. I mean, it's not that big a deal, and it's in all kinds of tables. All you got to do is go look one up. But I want us to do a couple of them so you see where the tables are definitely coming from. So the reaction at 1, yes, sir? All those ones are A's. Yeah, every one of them. How many more did I miss? Delta A, yeah. Delta Q at A, delta Q at A. I mean, take your choice, you know. I really need the A's and the B's because in the slope deflection method, that's what he's got all over the place. When you're doing the flexibility method, it really makes sense to label all unknowns, R1, R2, R3, R4, R5, R6, R7. I don't care if they're right, up, left, down, horizontal rotation. It just makes your life a ton easier because things move all over the place. In the method I'm getting ready to show you, that isn't, you'll see what we do in a minute. Using letters really makes your life easier in that case. And how many more? I don't know. That may be most of them. Delta A, R sub A. Down in the equations, delta at A should be 0. The reaction at A is given a number. Thank you. All right, now if anybody got any question, or if you can't solve for how much reaction is generated on the end of a cantilever beam that's propped because you put a moment on it, shame on you. You ought to be able to do that. Take the reaction loose, put the moment on it, find out what the moment diagram looks like, put a unit load times R sub A back on it to make that problem disappear. Set the total deflection equal to 0 and solve for the reaction at A. All right, now then there are a set of these tables available to you in the text on page 476, but I don't think you'll ever find them. So he put them on the inside cover. Here, for example, is the case that we just did. This is the moment at A with respect looking towards point B. Now the moment that he puts on there is a special moment that he wants to get in terms of theta. I don't know. Does that help? Okay, thank you. The moment that he puts on there, just like the moment you and I put on there, the only thing is I solve for m sub AB just in terms of theta. If he wants to put this much theta on there for some reason, and he does, then he's welcome to do so. For example, when he puts this much moment on there, he gets a unit rotation out of the end of this thing. And if you'll stick our moment into this equation, you get the same reaction that you and I got. For example, he says, if you don't mind in this table, I'm going to use it for slope deflection. I said, fine with me. He says, therefore, I'm going to tell you how much moment you get on the left-hand end due to a unit rotation on this end. He says, fine with me. I said, doesn't look like what I put. He says, well, stick mine in there and see what you get. If you insert for m sub AB 4EI theta over L for the moment, then the reaction would be 3 over 2L times how much moment you want to put on there for some reason of your own use, 4EI theta over L. Then 2 cancels into the 4. You get 3 times 2 is 6. EI theta over L squared for the reaction. 6 EI theta over L squared for the reaction. 6 EI theta over L squared for the reaction. It's fine with me. You'll see what this one is used for shortly. All right. Now then, we found the reaction generated when you put a moment on here. Oh, these are called AB. That's good. What I want to find now is how much reaction you're going to get out of it and the moments on the other ends. 3m sub AB over 2L. Darned if I didn't solve for that. Maybe not. No. Put the moment on there. Get this reaction out. Get this reaction out. Yeah, I know what I'm going for. I'm going for his number on the inside cover. I'm going to tell you that I'm going to apply a moment on the end. It's going to cause some angle theta sub AB. It's going to generate this reaction that we just found, 3/2 of m sub AB over L. 3/2 of m sub AB over L. And I'm going to show you the moment diagram caused by both of these people on your cantilever beam, separately, one at a time, because of the moment AB. There's your moment AB. Here is the moment due to your concentrated reaction. The total moment diagram for those two things put together, if you want to do them by pieces, it's okay. But I'm just going to go ahead and turn them into one moment diagram. The moment diagram will have this height on the left-hand end, m sub AB. On this end, it'll have a positive m sub AB and a 3 m sub AB over 2L times L, which is 3/2 of m sub AB down, plus m sub AB up, 3/2 down, gives me a negative moment on this end of m sub AB over 2. Let me take these off. I was using them just so I could use my volume integrals. I'll put them back on in a minute when you need them. Now then, if you put m sub AB on this end, if you replace that instead with a 1, the only difference is the MAB will turn into a 1. And what I want to do is I want to solve for theta AB. In other words, when you put a moment on this end, my question is how much theta sub AB comes out. You haven't told me that yet. Over here, you found out how much reaction is necessary so this thing doesn't move up and down under the action of your moment. But you never told me how much the final rotation of the end of your beam was. That's what I'm looking for now. So I have a real load, a real moment diagram, and I have a unit load, and I have a unit moment diagram. Obviously, if m sub AB simply goes to 1, then the moment diagram looks the same. The only difference is instead of being MAB on this end, there's a 1 on this end. And instead of being MAB over 2, it goes to 1, so it's a half on this end. And what I'm going to do is I'm going to do the same thing we've been doing now for weeks. I'm going to integrate the m sub AB due to the real loads with the moment due to the unit loads caused by a unit moment. That ought to give me the rotation. I don't understand you guys. What is it? Daylight savings. Still, I don't believe that. I guess it's a good question. So, in other words, these people think they're here 40 minutes early? All right. Therefore, if you would like, write me an equation for the real moment diagram, write me an equation for the unit load diagram, and integrate MMDX over EI. Now, you're just doing that to fake me out, aren't you? Because I know you were already here. Or use volume integrals. I like volume integrals. All I have to do is take a trapezoid with a trapezoid, and here's the equation right here. I have to be careful with the signs because all of his are shown above the line, so all of his A's and C's and D's will be positive. If one of the values goes below the line, then I'll have to call that a minus. So I want LA, let me factor out the L, that's L over 6. There's an EI because this guy really is not for deflections, he's for volumes. And then I would have that onto A, onto 2C plus D, plus B onto C plus 2D. That's what I have here. L over 6 EI, and this will be one of the trapezoid heights in combination with the moments on the other end. So we would call this guy M1, this guy would be M2 for use in the volume integrals, this guy would be M3, and this guy would be M4. Don't forget that M2 is a negative number, and don't forget that M4 is a negative number. And then rather than have to write equations and do the integral from 0 to L, all I do is I just drop it in the equation. It is L over 6EI times M1 is MAB onto 2 times M3, 2 times 1 is 2, plus a minus a half, plus the second end of the real moment diagram, which is a minus MAB over 2, is a minus MAB over 2, times M3 plus 2M4. M3 is 1, plus 2M4 is a 2 is a minus a half, and so this term is going to be 0. It's going to be 1 plus a minus 1, so that's a 0. So the only thing I'm going to get is this piece right here. It says, let me move the 6EI on the other side, 6EI theta AB divided by L is equal to just this piece right here, which is M sub AB onto 2 minus a half, that's 1.5, so divide by 1.5. Now I know. If you decide you would like to crank theta AB to some number of radians, this is how hard it'll be to do the job. This is how much moment is on that end. And then that's what he's got here. 4EI theta AB over L. 4EI theta It doesn't say AB, it's on the AN divided by L. All right, now let me show you a summary of all of the moments that happen whenever you twist a structure. I'm going to say, for example, here you have a structure, and it is pinned, and it is pinned, and it is pinned, and maybe it is fixed. I'm going to tell you that if you come in here and force a theta on one of these joints, that I can tell you how much moment it's going to take to do that, and I'll tell you how much moment you'll induce over on the other end of the piece of steel. This is pretty much summarizing what you and I just did. If you want to take a fixed structure and roll it some number of degrees, some theta, here it is right here, the amount of moment it'll take you to generate that theta is 4ei theta AB over L, where this is A and this is B. On the other end of the structure, I'm going to cheat. Be easy enough to find out. Be easy enough to derive it. Here's how much moment it takes you to rotate this thing an amount theta. What's generated on the other end is 2. It's half. It's 2ei theta over L. I guess we didn't have to cheat to do that. We knew it from this, didn't we? If you put M sub AB on this end, you get half on the other end. So that really came out of the other work we did. Didn't need the book. So if you rotate this joint some amount theta, that's how hard it'll be to do the job, and the moment induced on the other end will be half of that amount. Now, if you look at that from the other side, and you rotate end B instead of end A, all you got to do is turn this sheet upside down. It's a little hard to see now, but if you could see through there, here's what you'd see. You'd see somebody cranking clockwise on this one, being a 4ei times how much theta you want to cause at that end over L, and half of it will come out over on this end. M sub AB will be on this end 2ei theta B over L. Can do the same thing for a beam that gets moved vertically and you don't let either end rotate. Cheating. Here's the answer. If you deflect a beam down an amount delta, in order to keep these things straight into the wall, it'll require a 6ei delta over L squared on both ends in order to keep theta sub A and theta sub B equal to 0. And I have shown the moments always clockwise. The book shows them the way they really go. The only thing is we're going to have to come up with a sign convention, and here's going to be the sign convention. Right, there we go, slope deflection. The name of this method is called slope deflection. Good morning. What's that?
I wore flip-flops.
You work for somebody?
I wore flip-flops.
Oh, you wore flip-flops. I see. Now, while I'm watching for you, I mean, past 50 minutes, I always kind of watch for you. Here's our sign convention. Arbitrary? Totally. Everybody else uses it? totally. Using a slope deflection method to solve for these answers, you'll see how in a minute. If a moment is clockwise on the member, we'll call that a positive moment. That means that, although you'll always have the member there to look at, but that means that a positive moment on the joint, those will be counterclockwise. And we'll call them that no matter which end they're on. I don't care if they're on the left end or if they're on the right end. That's a positive moment on this member using slope deflection. This is a positive moment on that end. By the same token, if you have a rotation of the joints on the end of the structure, we'll call them positive if they rotate clockwise. And finally, if you have a member where you have some deflection of one of the joints with respect to one of the other ends, if the right-hand end moves down with respect to the left-hand end, with obviously the connotation left end goes up with respect to the right end, we'll call those deflections, those clockwise tendencies for these joints to be separated in a horizontal plane, positive.
Howdy.
Howdy. I think you're paying these people. I really do. I think the guy who comes in last gets $100 and y'all have all chipped in. No?
I'd show up a lot later if I was
All right. Now, there's my sign convention. That's why I'm going to show all of these things shown on here clockwise, even if you know better. For example, you know very good and well if this thing goes down that it would look like this if you didn't hold the ends horizontal. And you're going to say, well, that isn't right. And you're going to say, I know I really have to crank on it this way in order to get it back so I can get it horizontal into the wall. And the same way with this end. If this end moves down, if that's called a positive deflection, the moment it would take for this one right here would be counterclockwise to push it down so that it could come back into the wall. That's the way they really go. You'll always have to know which way they really go, so you'll know whether or not you're supposed to call them positive or negative. But I want to make sure that you know that this is positive. If you didn't do that to the beam, then you'll enter that number into these equations as a negative number. So I've got what's going to happen to you if you roll this right end. I've got what's going to happen to you if you roll the left end, the right end. I've got what's going to happen if we deflect the beam one end relative to the other. The only thing I don't have is I don't know what the moments are going to look like when you put your loads on there. I mean, it depends on if they go down, it depends on if they go up, it depends on if you have concentrated moments which go clockwise, counterclockwise, whatever. I just have to leave that to you. But as always, if when you put the loads on the member, let's just say you put this load on the member and you put this load on the member. When you put the loads on the member, if on the member you have to roll clockwise, you should enter those numbers as positive numbers. So for example, in this case, let me go ahead and just let whatever's going to happen. That would go up like this. I would tell you that this moment, I don't want it to be able to roll this end of the beam. You would push this direction on the beam in order to make it come back out horizontal. That would be a positive or a negative moment. Positive is correct because it's clockwise on the end. On this end here, you'd have to do that. That would be a negative moment because on the end of the beam, you're cranking in the counterclockwise direction. All right. What happens is in the slope deflection method, a piece of paper with it on it somewhere, it'll be just easier to do it again. 3A. You're going to not call the reactions as the unknowns, and you're not going to turn the structure into a released structure or a primary structure. Here is the original problem as an example. And what you're going to do is you are going to tell me what you think the loads. What the loads do. And let's just say there's a load down here, and let's say there's a load down here, and I don't know how it deflects, but I'm going to tell you that I think I know it deflects something like this. I know it goes through that point. Evidently that load there wasn't big enough to get that thing back down. Got me. I'm going to tell you that rather than having the reactions as the unknowns, I'm going to use the slopes of these beams as unknowns. If this is point A, and this is point B, and this is point C, and that's point D, I'm going to tell you that what I say I don't know is theta at B. And I'm going to tell you that I don't know theta at C. And I'm going to tell you that I don't know theta at D, as opposed to the reactions. Now, one thing nice about that is I don't have to come up with a primary structure. I use the real structure. The thing that's bad about that is the unknowns are a little less obvious. For example, I know one thing. I know theta A. I know theta A is 0. But I don't know theta B, and I don't know theta C, and I don't know theta D. That's what the slope deflection method uses. Now, I'm going to tell you that for any structure, I don't care what it looks like, and I don't care what the loads look like, this is how much moment you could generate on end A of any member with end B over to the right. First off, I would ask you, did it have some theta sub A? And you might say, well, could be. Well, then if you had some theta sub A, I'll tell you how much moment was on end A. It's 4EI theta A over L. 4EI theta AB over L. Or just, I think the book just uses theta A. I don't know, I kind of like AB so that you know which span you're in. For example, look at this. Here's theta B. If you're looking that way, the angle is the same on both sides. But if you're looking this way, I'm going to be looking for loads inside of this span. If, on the other hand, you're looking back to the left at A, it might be nice to call all this stuff BA so you know that we're talking about things in that span as opposed to this span. Can't hardly go wrong with this. We already worked that out. We found that if you have a theta at A, the moment on that end is 4EI theta sub A over L. Now then, let's say that your beam had some theta on the far end, as did this one right here. AB had some theta on this end. Theta sub B, when someone made that theta B happen, I don't care with a concentrated moment, I don't care with a load down here which caused this thing to deflect, when you rolled this end, you caused some moment on the other end. How much moment you caused on the other end was half. It actually looks this way. In other words, if you put some theta sub b on this end, you caused some moment on this end, which is 2ei theta b over L. So I got two people causing moments at joint A in span AB. 4ei theta sub AB over L plus 2ei theta sub BA over L. See why they're both plus. When this one went clockwise, the moment was clockwise. When this one went clockwise, positive rotation, you had to crank clockwise to keep this thing in there horizontally. So they're both clockwise on the member. Next, how much moment do you get if the right end goes down with respect to the left end, causing a positive delta? If your delta goes up, not a problem, reverse these signs. If it goes down, you had to really crank this direction to hold it up. That's not a positive moment at that end of the member, and therefore the moment is equal to 6ei delta over L squared, except it'll be a negative on that end. And there's your negative 6ei delta at B with respect to A divided by L squared. And this last number I can't help you with. If you put any loads in the middle of the member that cause some moment at A, you'll just have to tell me how big they are and which way they go. And how you'll do that is you'll look up in a set of fixed end moment tables, just like that one. For example, I'm not sure I really like this, but I don't know if there's any real good way out of it. Here is a beam that's fixed on both ends, got a load P in the middle, causes some deflection that looks like this. The truth is the moment does go that way in order to stop this thing from rolling to the right. And because he knows what you're going to use these tables for, he's desperate to remind you to enter this moment as a not clockwise on the member moment, namely negative. The only thing that's always bothersome about that is anytime you see an arrowhead with a minus sign on it, some people are going to take it to mean the arrowhead is incorrectly shown. It really goes the other way. And that's not what this minus sign on this table means. He knows you're going to use these fixed end moments inside of the slope deflection method. He wants to make sure that if your load goes down, you enter that FEM as a negative PL over 8. Now, right now, you probably say, I see what he's done, but I don't know how we'd solve with anything, for anything with this mess. Oh, yeah. Let me simplify the equation a little bit. And not only that, let me correct that equation a little bit. M sub AB is I'm going to take 2EI over L out as pretty much common to all these terms. So that's 2EI over L times 2 theta sub AB. The book just calls it the theta at A. There's nothing wrong with that. It is the theta at A. But this fixed end moment is in piece AB. Plus 2EI over L times theta at B, looking back towards A, minus, here's the 2 times 3 is 6EI over L, theta sub BA over L, plus the fixed end moment at AB. That has to be your doing. And then if you go to the other end, all it does is you go to the other end and all the ABs become BAs. All the This becomes AB, and this becomes the deflection on the other end, which is the same, and then the fixed end moment on that end. The book likes to summarize them, so you only need one equation. He says the bending moment in a piece of steel, guaranteed, will be this big. You tell me the theta on the near end, looking towards the far end, to the right or to the left, times 2EI over L, plus the theta on the far end, times 2EI over L, minus 3, and I don't know if you need that. All this is the deflection over L. In other words, if one point of the beam goes down to here, and that end of the beam is, you're told, goes down to here, then this is the delta, the relative deflection between the 2 points, and this is L, and he likes to call that angle delta over L. He gives it a symbol. I think it's harder to remember what that is than just to remember delta AB over L. All right. Now, rather than let you see that whole thing, I'm going to do it from scratch. Page 6. Here is the problem that I'm trying to solve. I have a cantilever beam with a 16 kip load on it. The length of the beam, 18 feet. Could I solve that using flexibility methods? Yes. Could I take loose the right reaction and let it deform, unfortunately? Yes. Could I then come back in and put a reaction on the right end of the beam and pull it back up so there's no deflection on the right end of the beam such that it deflects like it's supposed to in the first place? Yes. There's more than one way to solve for these problems. Most students' tendency is to say, look, just give me one and let me learn it and let's just do it that way. Well, it turns out that sometimes if you use a flexibility method, you'll have 40 unknowns. Whereas if you use a stiffness method, like the slope deflection, you'll only have 3 unknowns. You need both of them. Computers are wonderful at stiffness methods like slope deflection because they need no brains. They just flat say, tell me where the joints are. You tell him where the joints are. He finds out how much moment and rotation each joint causes. In other words, his primary structure, the structure he analyzes, is given at that point. Whereas you, when you have this problem, there are a myriad of potential primary or released structures. You could release the 3 in the middle. You could release the 3 on the left end. You can release the 3 on the right end. You can release this one and this one and this one. You can release that one and that one and that one. There's no number. And the computer that you can't do. And the computer goes nuts. You don't have any idea how to just even get started. So stiffness methods are used by the computers. All right, here is your beam. I'm going to separate it out from all of the supports. I'm going to put a moment on this end. Let's call this point A, call this point B. I'll call this the moment at end A looking towards B. I'm going to call that the moment on end B looking towards A. There's a shear. I didn't use it in any of the equations, but it's there. And there's generally a shear. And here is your 16 kip load. And there's the 9 feet and the 9 feet. So you see what I've done is I have separated out from all the things that are connected your piece of steel. and I'm going to write an equation for how much moment has to be at AB in terms of theta A and theta B and the deflection at end B with respect to A. Already you know a few things. What is theta A? 0. What is theta B? You don't know. Neither do I. What is the deflection of end B with respect to end A? 0. If the guy told you this settled down a half an inch, I'd just say it's a half an inch. Here are the equations. Blind allegiance to the flag. You just start writing it down. Here's the generic equation. The moment on the near end of a piece of steel, looking towards the far end, is equal to 2 times the modulus of elasticity of the material times the moment of inertia of the beam divided by the length of the beam times 2 times the theta on the near end looking over towards the far end plus the theta on the far end looking back towards the near end minus 3 times the deflection on the far end with respect to the near end divided by L, and then please add any fixed end moments inside of the beam on end A looking towards end B. Well, I can do that because I didn't ask me to do anything. I've already done all the work. The moment at A looking towards B is equal to 2 times the modulus of elasticity. Trying to remember if he actually gave us a number. I don't think so. Times the moment of inertia divided by the length of the member. Let's just stick in the length of the member. It's 18 feet or 18 times 12. On to 2 times the theta of the near end A. Let's see, now I'm ready to put letters in here now. Theta at A looking towards end B. Would you tell me theta A looking towards B was? Well, I'll go ahead and stick that in there now. Plus the theta at B looking back towards A minus, you told me that deflection was 0, plus, well, now I got to go do some work. Now I got to go take a beam. I got to put a 16 kip load on it. I have to fix the ends so that they don't rotate. And I have to determine how much moment is caused by the 16 kip load on this beam due to this load. I've already got how much moment is on there due to rotation of the ends and translation of the ends. All I don't know so far is this. The real moment is going to be this way because it would like to deflect like this, except you got it fixed into the wall, so I'm going to have to push this up so that it does not roll at the wall. And the magnitude of this moment at A, fixed end moment at A looking towards B is equal to, Carol, how much? Got a book? Okay, has your buddy got a book? There you go. Inside cover, right-hand side, look for a beam with a concentrated load in the middle. Look for the answer on the left end of that picture. That's correct. So the fixed end moment plus the fixed end moment is a minus PL over 8. Believe it or not, there's one equation. And unfortunately, it's got a couple of unknowns. It's got a theta sub BA, and it's got an M sub AB, and some P is known and L is known. Equation 1. Now then, I pick up and I walk to the other end of the beam. That's M sub BA. I was standing here, looking that way. I'm now standing here, and I'm looking this way. And I don't know what I'm doing, and I have no idea, but I know one thing. There's a moment at that point. And that moment is because the following things happened to the beam. Number one, some jerk rolled this end, and he rolled that end, and he deflected the two ends relative to each other, and he put a load on it. And that moment is given by this equation. MBA is equal to 2EI over L onto 2 theta sub BA. Incidentally, if I ever write a number here that you know, tell me and I'll stick it in there now. Oh, gotcha. Do you know theta at B? Well, okay, that didn't mean L. I meant something major like the theta. And I was waiting and waiting until somebody took the bait and said, well, he thinks it's 0. But you did know this one was 0, but we don't know what this one is. So I just have to leave it theta BA. Plus theta AB. All right, I'm waiting for the guy who told me a minute ago, but he's kind of shy now. He's not going to tell me twice. But you're right, that's a 0. Minus 3 delta Fn, that's 3 delta B at A, looking, that's A with respect to B, divided by L. That deflection, the relative difference in height between these 2 points on the beam is 0. And then plus, and you put the fixed end moment right in there. Are you sure it's a negative? I'm sorry, where are you getting that negative? For BA, yeah. And if you look on the inside cover, you get a PL over 8. And as I say, in his zeal to make sure you'll know what sign you're supposed to use in these equations, he puts the sign on the page. And it is a plus. Now, wow, look at this. We got an equation for M sub AB. We got an equation for M sub BA. We got theta sub BA. Let's solve for theta sub B. Wait a minute now. Now let me go back here. Let me make sure we got all of these. M sub AB. Did you know this? Should I put a number here? No? Well, I think you're right. I don't think I know that. Theta AB was 0. If you look at your deflected shape, you put 0 slope. So that's a 0. Theta BA can't help you. I don't know what it is. Could be something even if it is a 0. And then there was no deflection. Here was a fixed end moment. M sub BA. Anything you can do with that? It is 0, isn't it? It's on the free end of a beam. The moment at this point is 0. Why? Well, because there's just air out there. In other words, the original problem looks like this. And the boundary conditions are that there's no rotation at A, and there's no moment on the free end of that beam. There is probably a reaction, but that reaction has no moment arm, and therefore there's no moment there. So this number here was able to be set to 0. And then this theta we already agreed we didn't know. This one we knew was 0. That deflection we knew was 0. And the fixed end moment was PL over 8. That's equation 2. So we have 2 equations, and we have 2 unknowns, and so we ought to be able to solve for everything we need. This equation right here is as good as any. It says that theta sub BA is equal to, that's a positive, this will go on the other side, is a PL over 8. And then that will be multiplied times the inverse of this, which would be L over 2EI. Is that right? I think so. So here, yeah, M sub AB, thank you. All right, M sub AB, L over 2EI is on this side to be multiplied on the other side, PL over 8. All right, so M sub AB PL squared over 16EI. I got all the math right finally. All right, the other equation says that theta sub BA is equal to, yeah.
How did you go from, shouldn't it be lower to make it plus PL over? Yeah.
Right. Let me solve for the other one, the one I got here on next to me. Thank you. Solve for the easy one. This one. Do it a piece at a time. 2EI, 2 theta BAL equals minus PL over 8. You solve for that theta sub BA. Theta sub BA equals minus PL over 8 times L divided by 4EI all right, I can live with that. PL squared minus 32EI. Now that's what I'm looking for anyway. That way I don't have to have it in the equation. Here's the moment AB. M sub AB is equal to 2EI over L times theta BA. Theta BA is a minus PL squared over 32EI minus PL over 8. EI cancels EI, 2 cancels 32 with a 16, L cancels L is equal to minus PL over 16EI, over 16, minus PL over 8 is 2PL over 16. Final answer, minus 3PL over 16. That's what I was looking for. Moment in the beam. Why am I looking for the moment in the beam? So that I can design it. Believe it or not, that's right. Yes, sir. Well, the P is just a number, so the P is just 16. You took care of the sign when you said the load went down, and when you looked in the book and you looked at his fixed end moment and he had the load down, there's where those signs worked out whether the load is up or down. All right. Now then, here's what your beam looks like. Your beam has a 16 kip load on it. 9 feet, 9 feet. It has a shear on the left-hand end. It has a, I don't know, who knows which way it goes. BA. We don't really have a sign convention for shears in the slope deflection method. You just stick them on there, and whichever way they come out, if they're right, you'll get a plus sign. On this end of the beam, there is a moment. His name is M sub AB. He is a 3PL/16 with a minus sign in front of him. Which way do positive moments go on these beams due to our sign convention? Clockwise. Since this guy says minus, that means that this moment really goes 3PL/16 to the left. And of course the moment on this end we know was 0. Now then I ought to be able to put that in equilibrium. Some moments about A is equal to 0 is equal to plus 3PL/16. I like this sign convention for statics. It's up to you. As long as you're consistent, you're okay. Plus 3PL/16 minus 16 times the moment arm of 9 feet plus the shear at B looking back towards A times 18 feet. I need some help with a calculator here. That says the shear on the right-hand end of the beam is equal to 3. On the other side is a minus 3. The load was 16 kips. The length of the beam was 18 feet. Divided by 16 plus 16 times 9. Whole mess divided by 18. Whoever muttered, shouldn't it be? Yeah, probably should be. Tell me now. All right. 5. Total 5. Just plain old flat 5. That's strange. 5 kips. And you're saying the 16 times 9 beat up on these guys here. And you're probably right, because 16 cancels 16, and 3 of them's 20 is about 60. And 9 times just 15 is 100 and something, so you're right, plus 5 kips. That means this guy is 5 kips big. And that means that this guy is 11 kips big. And who cares? I care, because now I can draw, shut up, a shear and a moment diagram. Up 11, nothing going on. Down 16, nothing going on. Up 5. There's my shear diagram. Now my moment diagram. Yes, sir? Hey? Oh, thank you. How'd that happen? Thank you. Now then, my moment diagram. What do you do when you cross counterclockwise moments? Do you jump up or down? Well, that's pretty good. Everybody says down, and that's correct. Here is a picture of it. Here's the end of the beam. Here is that 3. We'll have to work out that 3pl over 16 is equal to 3 times 16 times 18 divided by 16. That won't be hard. That's 60 minus 6, 54. Right. That's 54 kip feet of moment. You see how the moment starts on the left-hand end of the beam, causing tension on the top and compression on the bottom. So as this thing first gets into the beam, it causes a negative moment. So you jump down 10, 20, 30, 40, 54. As you cross this area, you cross 11 times 9. That's 99. 54. 99 higher than you used to be is 45. Thank you. Is 45 kip feet. Straight horizontal lines turn into straight sloping lines. This is 5 times 9. Ha, that's nice. 45. There's your moment diagram. When you get into 444 or when you get into concrete, you'll start talking about designing the beam to resist these moments and these shears. Anybody still awake? You lie. Of all the people who weren't awake, it was... All right. See you next time. Yes.
This load was in the positive direction. Would you draw the fixed end moments in the counterclockwise way?
I would. Yeah.
Okay, so it's not.
But the book says, look, I've taken that into account for your students. If the load goes up, he should enter the terms.
They're the quizzes from us.
How come you didn't put them at the beginning of class? Huh?
I didn't think about it until I sat down. I had to help Sandra and practice track.
Did she say anything English in that sentence?
She had to sit down because she had to help someone with a truck.
Yeah. I didn't think about it until after I turned in my homework. I did myself.
Gonzalez? Is that you?
Yeah. I was helping Zollinger.
And did you hand in Carol's sheet?
No, I handed in Carol's.
And why didn't? Where's Carol?
Here it is.
So he was back there and he gave you his quiz so you could copy it? No? Well, why didn't he hand his in at the beginning of class?
I said I'm going to go hand, I don't know, because I reminded him to turn his in.
Carol?
Where you at?
Well, all right.
I was helping Zollinger.
You were helping Zollinger.
We got bricks today. I have dirty shoes to prove it.
Okay, don't bring somebody else's papers up at the end of class and expect them to be graded, okay? Ah, jeez. Yeah, go ahead. What?
I was talking to you.
Oh, yeah, I'm sorry. So when you put the load that way, see how this guy will change sign and he'll change sign?
Yeah.
So you'll enter him as a plus and you'll enter him as a minus.
So I would change the convention to where this is counterclockwise then.
That is correct. In other words, when you push up on it, the truth is you'll have to crank the other way in order to make the thing come parallel into the walls. That doesn't look like it got across. I'm not sure.
No, I got it. It was just when you were talking at the beginning of class, you said they should both be clockwise most of the time.
That's right. In other words, it's not a matter they should be clockwise. The sign convention calls for this to be called positive and that to be called positive. Now, if you do this to your beam and it wants to do this, and you have to do this to make it come out straight, and you have to do this to make it come out straight,
Right.
then you should enter the number listed here, regardless of plus or minus or what. You should enter that as a negative number because it's not clockwise on the member. In other words, these are positive. That's the sign convention we used when we derived all that stuff.
Is that just for this method?
I'm
Is that
sorry,
just
it
used
is
for-
indeed.
Okay.
I know you have a sign convention for statics. You have a sign convention for internal moments in shear and bending moments.
Okay.
You have a sign convention for shear moment diagrams. You have a sign convention for slope deflection.
Okay, so
You have a sign convention for Moore's circle.
heaven forbid we had to make a cut here.
Well,
Now, what would our sign convention be on the end?
well, now that there is none. In other words, the only sign convention by this method gives you moments on the ends of the member.
Okay.
So now then, if you were asked for the moment at this point, you will have to come and do all of this work, find the shared moment diagram, and then when he asks you for the moment at this point, you'll pull it off of the diagram.
Okay.
Or you'll multiply the shear times 4 feet or whatever it is and get the moment.
Or just skip the question on
You'll skip the question.
Just got it nice.
No, that's not necessary. But you see, slope deflection doesn't give you anything about what's going on inside. He only tells you answers on the ends of the members.
And then, like, you gave us this.
That's correct. That's positive.
That's a cut. Isn't it?
Well, see, it's the guy who's attached to this little piece right here. It's a joint. Okay? So if someone went this way, as you know our sign convention calls for, then he did this to the joint. I got one yes out of 2. That's not bad, and one uncommitted.
So are you making a cut, or are you?
Yeah, we're cutting at the end of the member, and we're exposing the moment inside of the member, and that's what slope deflection tells us about,
Okay, so
that moment.
What you drew on that other, where's that other page?
Go right ahead.
So
This one here?
this is an internal cut.
That's an internal moment inside. That's correct. And that's connected to this guy here. See, it's another piece, and there's another piece over here, and there's another piece over here, and there may be another piece down here. But if somebody did that to your long piece of steel, your long piece of steel did that to the joint to which it was connected.
Okay. So we're putting arbitrary walls, like right here.
Yeah.
On both ends, arbitrarily.
Well, that's correct. That's
And we're
correct.
dealing with internal walls.
That's correct. Where was the original problem show up? Here was the original problem right here. And I'm not sure about arbitrary walls. I guess we are putting walls on it, because it's a stiffness method. But you're solving for the moment right there, just to the right of the wall, and you're solving for the moment right here, just to the left of that pin. And that's what we drew, see? We drew that right here.
And if we don't know which way it's going to bend, we'll say something crazy.
Well, you don't know. You can't tell.
How do we know? How do we know whether our MBA or our MAB is reversed?
You will know that because when you get the answer, guess what? It was reversed.
Okay.
Because you got a minus sign for the answer. That means that I showed you the moment on the beam in the positive direction before I had analyzed it. It turns out that this beam would like to bow down like this, and you had to really do that to it to make it come straight into the wall.
Okay.
As opposed to what I initially thought. But you can't hold me responsible for a guess before we analyze it. I put it on there in a positive direction. Turns out the moment is actually a negative number. It really goes the other way.
Is that why our theta BA came out negative?
Theta, well, now that's on this end.
Okay, so this should actually be going down?
Well, I don't know. We've got to go check our sign convention. Here's our sign convention. Here's our sign convention. I know the answer.
You're going to have fun on this next test, aren't you?
Well,
This isn't until the final.
Bend over, guys.
here we go.
According to the schedule online, this isn't until the final, so
Really?
it's chapter 12. So, yeah, chapter 12. No, we got 18 2 weeks.
There we go. Which way do thetas, which way do they go if they're going to be called positive?
Oh, I forgot about the theta convention.
That goes clockwise, doesn't it?
Right.
And guess what? Lo and behold, you found theta BA, was a negative number, which means it did not roll clockwise.
Minus 15 points.
Well, no, but I mean, there it is. But you know which way it rolls. I mean, you can just tell from drawing the deflected shape.
Okay. Gotcha.
All right.
And I missed this part as well. This is if the structure
That's right.
sinks, or
That's right. Let's just say, for example, that you had a structure that looked like this. And maybe there's no load on it at all. And the guy said, we have found that this is a soft soil, and there's not any doubt in our mind that this point right here is going to settle an inch.
so whereas with the previous method we add that on.
That's right. In this one right here, it's added in right at that point.
Okay.
It's added in as a delta of that end with respect to that end.
All right.
Question?
So, did you take off half a point for everybody that tried to play today?
No.
That's a lot easier question to answer.
A lot easier just to give the three people who are here on time a point.
It's A and D.
What is going on? I don't understand. I mean, I'm glad they're coming. I don't think I've ever seen a
I like
half.
the daylight savings.
The materials
Comment.
get dry.
Yeah.
So, this side convention and this side convention are both in the clockwise direction. Possibly.
That is correct. In other words, we really don't talk about the joints. It just so happens that if you're going to call that positive on a piece of steel, 9 feet in length, 30 feet in length, whatever,
Right.
then you have no choice but to call this
Right.
positive on the joint.
Okay. I was just checking to see that this is also positive.
That is positive. Now, that's an arbitrary choice. But we have decided to call, and you and I didn't, we didn't have anything to do with it. Before you and I got here, somebody decided that if the joint rolls clockwise,
I mean,
we'll
you
call
could
it a...
technically call it -2 and then still.
Yeah, oh, yeah, absolutely. And
Get
then
the
when you
same
derived
answers.
it, you'd get a reverse signs in every time you got a theta. Yeah.
Okay.
Most sign conventions are arbitrary.
Accuse you of using.